Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This talk is meant to be a tutorial, and I thank you for sticking around this morning. If you have some mild interest in understanding an approach to property extraction from programs or language definitions, then I'll try to make it worthwhile for you to understand how the abstract interpretation methodology might be just what you're looking for. And so, as a tutorial, I am going to make my way through what was stated in the abstract published in this proceedings. And so I'm going to begin with some basic examples, some definitions, and the important stuff comes in the first 10 minutes. Then we'll cruise through the middle part, looking at how you apply these things to different definition formats and how it's used in practice. And in the last part of the talk, I'm going to return to issues regarding properties as propositions. There are logics that you get when you define a form of static analysis. And we'll see how these things might scale upwards, which is really a tough topic, as of course all of you know. Scalability never comes easy. Let's begin with the background. There's going to be definitions and details on these slides, more than I can read, or maybe more than you can read, but I wanted these slides to be self-contained. You can download them from my webpage later and read the definitions if you care. But let's focus on the pictures. So in the upper right part of the screen, what I've tried to show is the integers. Let's say we have a program that takes an integer input and produces an integer output, and we want to test it, but there are too many tests. There might be just a subset we want to test, like maybe just 2, 4, 6, 8, but there's still infinitely many tests. How can we cover all of these tests? Well, this kind of question can be answered by saying maybe I can designate some tokens or properties that represent collections of the integer tests, and maybe I can run the program, test the program on the property tokens instead of the concrete values. So I've used, say, neg, 0, and pos. The sign of the integer might be significant to what I want to test. You can see I've arranged them, though, as a complete lattice, because what happens if in the middle of the analysis I can't remember anymore if the integer in the middle of the program is a negative or a 0, I lost track. So you have to use a token, any. It's the join or the weakening of information. And then, of course, dually there's a bottom element. None means no data at all or dead code. Now you see to the left of those properties, I've written out all these integer test sets. I've written a function gamma. Gamma is the interpretation function. It says what those tokens stand for. And so the token neg, for example, stands for the set -1, -2, -3 mumble. And what we'll see is that we're going to require that gamma does something special. It preserves lattice theoretic meat as intersection in the world of test data sets. That will allow us to define a kind of weak inverse in just a moment. But for now, think of gamma as telling you what the tokens stand for. So here's our program in the upper left corner. It's reading an integer, and we have these very strong suspicions that the output integer, regardless of the value of the input integer, is going to be a positive. But how long are we going to test it before we convince ourselves? Well, if I give it to my students, they'll still be busy doing it, but we won't go there. Instead, we're going to take this clever idea of executing the program with those tokens, neg, 0, and pos. That requires we have to reinterpret the assignment statements for successor, the negation statement in the original domain. We have to abstractly interpret them so they compute on these tokens. So we have to have a way of converting the concrete program into an abstract program that understands how to read one of these sign tokens and compute on it. That's an abstract interpretation. And you can see that I've proposed the abstraction of suck and negate in the middle of the slide. And negate really works like a charm, because it's easy to talk about what it means to negate a neg or a pos or a 0. There's a technical problem with suck. You can see that suck can be described as suck sharp, but what does it mean to take the successor of a negative token? I don't have a precise enough description language just now to say that when you add 1 to a negative, you get a non-positive. Somehow they got left out of my domain of properties. Boy, this is a standard practical problem. Lots of times when people want to analyze a program for a correctness property, they have a pretty good guess of what properties they should use, what tokens they should use to do the analysis, but they don't always think of all of them, all the intermediate values that might arise. So as simple and contrived as this example is, it's critical because it shows that sometimes your initial guess isn't good enough and you have to refine it. Nonetheless, we can go ahead and we can calculate these tests. And I calculate at the bottom of the slide the test for 0, the test for pos, the test for neg. I've covered all the integers this way, and I was unable to validate for a negative input that the output's positive. And that's because I lost precision right there. But you get the basic idea. It's a simple idea. You execute on the properties. So you're doing an abstract interpretation. Now, this was the idea Patrick Cousseau proposed in his PhD work, and he and his wife, Radia, developed these ideas over the decades, and almost all of the material I'm going to show you today was inspired by what they've done. And so this is really Cousseau presented by me. There are, of course, some interesting little angles on it, but their spirit is very strong in this. We're going back to this picture, and I've introduced a reverse map alpha. And alpha is what you use if you have a particular data test set and you want to find the token that most compactly covers that test set. So maybe I want to test that little program for the data 2, 4, 6, 8, 10, 12. What token best covers that data test set? It's alpha, because alpha will map all of those circled values into pos. So, oops, I'm sorry, we want the laser button. Where is the laser button? Let's go back to where I was, and let's push this button. So this set here maps to pos, but of course all of these do. The important point is if this test set is abstracted, and then I use gamma to go back, I get a larger set. So these are not exact inverses, but they are a weaker form of inverse called a Galois connection or a residuated residual pair. And of course, if you're a category theorist, you'd say it's a simplest example of an adjoint situation. So they work together. Yeah, Peter.
Just a trivial question. I mean, why don't you actually consider the least upper bound of negative 0 as being something different from any?
I'm going to add it later. I wanted to put this in just to point out the very practical problem that sometimes these things catch us. And in practice, it's extremely difficult to get all of these covered, say, for a really large program. You just can't see all the way through it. So yes, we will in a bit. But I wanted to bring up this point that imprecision sneaks in so quickly in this kind of work. It takes a real talent to design the domain correctly from the beginning. But yeah, that's a really important question we always want to address. So this is called a Galois connection. It's the first important point in abstract interpretation theory. If you set up a collection of properties, organize them as a complete lattice, have a gamma map, try to ensure, you should ensure you have an adjoint situation because you're going to win a lot when you build your implementation. We'll see what you win here in just a moment. Now that we have that, where did those suck sharp and negate sharp operations come from? Well, in an algebraic sense, they have to be related to the original suck and negate operations in a homomorphic way. But it's not an exact homomorphism, it's called a semi-homomorphism. Because if we write it out as a commutative diagram, which I did in the middle of the slide, what we see is the original operation, blue F, and in fact, blue F can take a single input and produce a set of outputs. So that means we can handle non-determinism, no sweat. Blue F has to be modeled by red F sharp, and you have to have the commutative diagram with respect to gamma or alpha. It's equivalent when you factor in that less than ordering on the complete lattice of the properties or the complete lattice of the sets of data test values ordered by subset. Either diagram works for you. And so in particular, if you pretend these properties are like propositions, it turns out that red F sharp is a postcondition transformer, since blue F is a function. What if you have an exact equality in your homomorphism diagram? Well, that's called completeness. At least that's what Roberto Giacobazzi likes to call it. And interestingly enough, if you have a commutativity with respect to alpha, if you have an equality here, that's different from having an equality with respect to gamma. You kind of sense that because these arrows are going in opposite directions. It's a little tough to first see why they're different, but remembering that the image of gamma turns out to form a collection of sets which is a closed family of sets like you have in topology, then Gamma completeness is what you get when you get a function that's a closed mapping, maps closed sets to closed sets in topology. And alpha completeness of a map F is what you get when you have a topologically continuous map, mapping inverse images of closed sets to closed sets. Later on, we're going to find that gamma completeness is super important for understanding the logic inside the lattice of properties. So that's why I wanted to mention that now.
The second thing you said, inverse image of closed sets, but it's probably inverse image of open sets.
Well, it turns out in topology, remember, it's equivalent. A function is topologically continuous if and if. It maps inverse image of opens to open and closed to close. We're doing an over-approximating analysis, so it turns out the image of gamma defines the topology of closed sets. When we move to precondition analysis and we want to have interiors, we'll end up with a topology of open sets. And then you get the standard continuity that's taught. So it turns out there's actually a surprisingly large amount of useful topology inside this stuff. But I won't be able to talk about that today. It's just cool stuff, you know. You take your algebra and your topology, and there it is. This is where program analysis comes from. So the second important point about abstract interpretation is that you have to have semi-homomorphisms. You can build those mechanically in the sense that the best abstraction of blue F is what you get when you take the blue F and you compose it inside the alpha and the gamma. And that gives you the strongest liberal postcondition transformer. And so that's your goal. Now, of course, in practice, what people do is they don't always get exactly this thing. But they come up with something which at least will do this commutativity stuff, which, of course, can also be defined in terms of the less than business. So that's the second important idea. So we're dealing with complete lattices, and we're dealing with these semi-homomorphisms. Now it's a matter of getting this machinery to work in practice. And so I've been working with the sign domain, but you know that real programs, they work with aggregates like storage vectors and arrays. And a lot of times the property you want to track is a relationship between elements within the aggregate. How do you state that? Wow, there's been a lot of work on that. Now in terms of the sign domain, let's say that, oh dear, let's say that we have some collection of storage vectors here which define X and Y. And it turns out that all of my collection there, my 15 storage vectors, the values of X and Y, they're all positive. Well, my little baby sign domain that I showed you 10 minutes ago, it will allow me to express that property. But notice the covering. I mean, wow, it's way imprecise. We ought to be able to tighten that up by at least stating the bounds that X and Y have. And that's called the interval domain. But what about the relationships of X and Y? Maybe X and Y are intertwined in some mysterious way. Well, there are some really cool abstractions similar to, you know, building convex halls. And one of the most useful ones in practice is called the octagon abstraction. Antoine Minet developed this. It's characterized by a set of linear inequalities where the multipliers are either 1 or -1 on the variables. And you get this really cool covering which always has 8 sides. And this was used by Antoine and the team at École Normale Supérieure to validate the absence of array indexing errors and arithmetic overflow and underflow in the 500,000 line flight controller of the Airbus Super Jumbo Jet. Airbus gave the Cussouds and their team a bunch of money to basically employ these techniques to check for these kinds of standard concerns, and they were able to do it. They mechanized almost everything, but then they took a couple of smart people like Antoine, sent them down to Toulouse, and they sat down with the engineers, you know, and it took them a couple of months, but they got through the whole 500,000 lines of code, and they said, you're safe. You can burn this into the chips, you can put this in the software, you're not going to have any worries. Yes?
Was it safe in advance, or did they find some bugs?
There were some errors, yes. There were some errors, absolutely. Were there any errors that were critical? I don't know about that. I don't remember that. They documented this in a PLDI paper a few years ago, and I bet you could find some of those answers there, Peter. So this is really useful in practice. I know the Boeing people in Seattle, they do these things, but they're much more secretive. So they won't tell you that they're doing these things. The polyhedron domain here is a generalization of the linear inequality, and the polyhedron works in a similar way. What's cool is about the octagon domain is that the canonical representation is a set of these linear inequalities, but Antoine showed that you can implement that either as little matrix values or little graphs. And you can actually pass those around as abstracted versions of arrays and storage vectors when you do this execution, like what I tried to show you about 10 minutes ago, 15 minutes ago on the baby program. Instead of dealing with a single variable and asking about its sign, you can carry around a little graph and keep track of the relationships. And so this is the key to making this technology work in practice. And if you're interested in inequalities and relationships, you got to ask the obvious question. Well, why don't I just model my aggregates, my storage vectors, my data structures by the inequalities themselves? And let those be the token values. And that's the basis of what's known as predicate abstraction, and that lives in the heart of these model checkers like SLAM and BLAST, which have been used to validate properties of device drivers. Because rather than mess around with whether a number is positive or negative, instead you use a language of inequalities. And the standard starting point, this little naive example, actually is really useful. Notice that I got some baby program and I want to ensure that the value of z is at least as large as x and y at the conclusion. I notice also there's an internal predicate that seems to play a big factor, and that's that one right there. So what I can do is I can outline those primitive inequalities, line them up as a little baby modeling, the value of this one, the value of that one, the value of that one, and then do a kind of what you call a symbolic execution. But it's actually an abstract interpretation, abstracting the concrete operations so now they operate on that triple of inequalities. And then I want to see when I hit the exit point whether or not I was able to validate what I wanted. And this one I did because my post condition is characterized as the conjunction of those two equalities. And so what you have here is an abstract model where the program points are annotated with these predicates. And then you can model check that abstract model. And that's what happens in BLAST and SLAM. You've got to be honest, though, that starting point doesn't always work out with a happy ending, and you sometimes have to augment the abstract domain, the properties, because maybe there's an internal predicate you couldn't see. And that's what happens in this baby example, where we're trying to validate a simple value that x is greater than or equal to y, but there's some internal messing around at program points P2 and P3. You can't see that at first, but you do find that the execution traces fail to validate the output goal when you go through the then arm. So what do? You have a heuristic, like I wonder why that failed right there. I bet if I can calculate the weakest precondition that would need to go through this assignment to get to my goal, I could find another predicate that I could add into this storage configuration. And so I reanalyze this path here, and I'm able to validate it. And this is also a critical part of the refinement that happens in SLAM and BLAST, because they almost never validate some kind of correctness property first time out. They go through this iterative process, and they may iterate forever, because I know that you realize, and you know from your own experiences, that you're not going to discover loop invariance in such a simple, handy way. And so this is just a reminder that the game that I've just shown you of starting with some starting inequalities and running them through and trying to come up with an analysis might not be able to validate what you want, because what you really need is a loop invariant. And so you can see that this iterative refinement would add lots of internal equalities and inequalities, but would never discover the loop invariant on its own. So you got to add a theorem prover or some heuristics or a human like Antoine to help you out. Yes, Srivan?
So you're talking about a CGAR-like process here.
That's correct. This is what most people, model checker people, call CGAR, counter-example guided abstraction refinement.
Right.
Yeah.
But there's sort of two very different things going on, right? One is the act of coming up with more predicates. These are sort of these hidden invariants that you're trying to discover, versus modifying the abstract domain itself.
Yeah.
Because the original example you presented with like the missing, the join of 0 and negative is really so.
Yeah. I think most people understand it the first way you explained it, but if I was Patrick Cousseau, I would say that you could then use that information, you could refashion the abstract domain and build a new abstract domain because it's implicit, because underneath it you have basically some sort of disjunctive normal form. You have a lattice of formulas in disjunctive normal form, and in each refinement step you throw a new primitive atom in there and you recomplete or rebuild the lattice of disjunctive normal form formulas. You don't actually build the lattice in the implementation. All this is done, of course, incrementally. And I mean, real analyses, no, they never build the lattices. It's all done incrementally. When we look at modular analysis, I'm going to say you build up the information in the modules incrementally, because that's how it's done in practice to scale upwards. Otherwise, you don't survive. But yeah, that's a good observation. There are those two philosophical viewpoints. And then Patrick would say, well, it's the same thing. But the first way is probably the way to think about it. I know that's the way Tom Ball would explain it. Yeah, yeah, that's great. Thank you. Anything else before we continue on? Okay, so I've shown you now the really critical parts. So even if this starts getting a little bit a little bit boring or mind-numbing, it's okay. We will come back to these same examples, and we're going to try to hit on some important points towards the end. But now I feel at least an obligation, given the nature of this meeting, to point out that even though I've been looking at the generation of traces, because all along underneath this was the idea, dear in the hearts of model checking people, that you want to generate execution traces or test traces, abstract interpretation is used to build a summary. This graph covers these kinds of test cases. There are other ways of doing it too. But this is where we are so far. Let's say that I have a domain, another baby domain, where I'm keeping track of the parity of an input integer, and this is the Collatz algorithm. And I'm wondering about the pattern where the input integer x is maybe flashing back between even and odd. How does that happen? Maybe I got some temporal operators and I want to check the alternation between even and odd. Good luck. But in any case, I can generate this abstract model because I start unfolding and then I get a repetition. Right here I get a repetition back to there, so I draw a backwards arc. And so this abstract model lies at the core of what most people call software model checking. You know, software is too big to really just grind it out and check these things. So people who really want to do validation using model checkers on software have to build an abstract model like this, and then they check, of course, the patterns of flow in that. You know, the bounded model checking people say, no, we'll just run it till storage fills up. And that's cool too. But in abstract software model checking based on abstract models, we're doing what I've been showing you so far. But data flow analysis is the origin of all this, because if you don't care about the fact that a program point like P0 starts out with an even number and 18 steps later reappears with some number that could be even or odd, if you just want to know what could arrive at program point P0, then your abstract model is the program flowchart, a control flow graph. And that's the basis of data flow analysis. When Patrick Cousseau was a graduate student, he started reading these papers like Kildall and Kam and Allman and realized that those flowcharts and all of that equation stuff was really describing this homomorphism property. And he wanted to tease that out and show there's many more variations than just ordinary first-order equational data flow analysis. But this was the starting point. And this is a very simple example of an abstract interpretation where we just write a set of first-order equations and we fold at the program points. And of course, all of that underlies the calculation with least fixed points, which is the third important principle of abstract interpretation, that once you have an abstract domain and you know how to abstract the computation functions to work on that abstract domain, then you want to do the computation and use fixed point techniques to get a convergence. And you want a finite convergence because static analysis means you really, really want useful information in finite time prior to execution. So it's not runtime monitoring. There is an issue of termination. If you use the interval domain, maybe you're checking the range of indexes of a variable that's indexing an array, you can have some trouble. And here I'm using an interval domain trying to keep the range of values of variable I in check so that I maybe don't abuse array A. In the interval domain, well, this one terminates thanks to that nice test right there. The interval domain would calculate inside the body of the loop at these program points that I is ranging like this, and on the exit we go to there. But it's easy to think of examples where you don't have the assistance of the test, and oh no, when you try to enumerate the range of values, you don't terminate. And so the Cousseaus pointed out from the beginning, when you set up that abstract domain, and it might have infinite cardinality vertically, not just horizontally, you need a heuristic to force a leap to a fixed point, to a stopping point. And they call that widening. And I'm just mentioning that we cannot escape the dangers of non-termination in these analyses. It depends on how you fashion that abstract domain. So when you calculate a least fixed point, you can do it in a finite number of repetitive steps. And so, of course, there's the religion of widening, and there's all sorts of stuff here I have to skip past because time runs faster than my mouth does. So let's look at these definitions. Now we can structure this stuff. We've done state transitions. Let's say your program's defined in a structured way. Maybe you used a grammar, and maybe you wrote straight-G equations to define how it is that an input storage vector is transformed to an output storage vector in that structured way. And maybe you've reformatted that. Oops, maybe you've I'm sorry, I'll get these buttons right by the end of the hour. Maybe you've reformatted that. So here's the abstracted version of assignment, abstracted version of composition. I'm ignoring tests on the conditional. The loop generates a local fixed point. I can abstractly interpret that, no problem. And what's cool is the abstract interpretation can be annotated on the syntax tree because it's attribute grammar-like, isn't it? That's no surprise. So here I went ahead and just defined as this example a reaching definitions analysis that you get out of any compiler text. And I annotate the syntax tree showing the abstract values going in and the abstract values going out. And in effect, I'm generating what you call Hoare triples for all the phrases of the program. And you'll generate the loop invariant in this way, or a loop invariant, I should say, when you get to the local fixed point that would arise right down in here, because you end up getting a set of repetitions when you try to get a convergent value right here for the while loop. And so the important point is, like we heard in the very first talk on Tuesday, if you have your computation and definition mechanism set up in a well-formed, coherent, concrete way, we're just doing a homomorphic translation from the concrete world into this world of properties. And we use the same underlying mechanism for semantics. And that's why it's an abstract interpretation as opposed to the original concrete one. And so now that you've seen that, then you say, well, oh, of course, that means if I've written my relational definition, I have multiple free variables, I can draw proof trees. And there's one right there. I inverted the proof tree into a goal tree for a big step semantics, and I read it from left to right, filling in values from left to right. And if I can do that in the concrete interpretation, I can do that in the abstract interpretation. And if I have an abstract domain and I know how to bound the range of values that can arise, I get, of course, a regular tree. That is, I get repetition and a backwards arc. And then I get another abstract model I can do property extraction from. And so it means that you don't have to fear that abstract interpretation is going to complicate your view of the semantic world. It's just using a homomorphism on what you have to a simpler collection of domain values. And so in practice, this has worked really well with interprocedural analysis. I'll have to skip past it. And in practice, it has been used, as I said, in abstract testing. We also have that when you are doing this kind of analysis, you can do lots of low-level checking. I know there have been analyses for object-oriented programs trying to keep track of the class values associated with constructed objects. So you can do pre-execution safety checking of casts to see whether or not they're reasonable. This works exactly as you would expect. And as I mentioned earlier, there's been a lot of effort working with device drivers, real-time software, monitoring bounds of integer variables to ensure absence of overflow, underflow, and array indexing errors. The Java virtual machine, of course, has a flow analyzer in it, which Patrick Cousseau would say is just a simple instance of abstract interpretation, which checks for dead code, does constant propagation analysis. You can do a lot. You can formalize a lot of the standard checkings in this way, because it's this general framework where you just plug in your choice of the properties, and then you use the homomorphism and the fixed point computation. Compilers, of course, they're based on data flow analysis. You do program transformation, working with the flow graph, tracking what values go through the program points to see if you can change the code. Yeah, all these applications are justified, are formally explained. The soundness of these applications are validated using the explanations from abstract interpretation. So in many ways, static analysis starts from this foundation, even though there are many variants on how it's implemented. With the 15 minutes I have left, I'm going to emphasize now more and more the synthesis and validation of propositions, logical properties, because that will be of interest to someone who's defining a language, defining a semantics, and wanting to understand if programs written in a certain way can be understood through the semantics as having these certain logical properties. And so starting from this, there's a baby program up in the upper left corner. And as Peter pointed out about a half hour ago, my original proposal for the sign domain was pretty weak because it didn't really have enough properties inside it. So I added a couple more. There are a couple of obvious ones that are missing. There's actually another one we could throw in. Maybe you can think about what that is. And I decided that I am very interested in whether or not, if this program must terminate with a non-negative number, what's required at the entry to ensure that? I want to calculate a precondition, a sound precondition. So I want to run the program backwards. And all of this really hairy, heavy technical detail is saying that these functions here can be abstracted in a forward sense, and then you can define the inverse image functions. And so lots of symbols, we can delight in these symbols, but the intuition is I'm just going to use the inverse image function on these abstracted versions of this stuff. Now, if I'm going to use inverse image functions, I'm going to actually start working with sets of properties, not just pos or non-neg. I'll be able to work with things like non-neg or non-pos, things like that. And that's going to become important in a bit. But anyway, pushing this backwards, using all this technical stuff, which can be, of course, automated, we can understand that the entry point is if the value is not negative. And the downward arrow means not negative, says, oh yeah, also if the entry integer is 0, or if it's positive, if it's nothing. Any of these will ensure that when you execute to the end, you'll get a value that falls under the range of being not negative. As a lot of compiler people know who do code improvement, sometimes you can take an entry precondition, you can run it forwards and get sharper information within the internal program points. And that's what happens here. And so the idea of iterating forwards and backwards is used in practice in code improvement modules. And it can be used here to show with this baby program that we learn by taking this as our entry condition, that when we calculate the exit condition, we find at this internal point something new, that x must be 0 at point P1, because now I'm running forwards. I'm bringing this up because I want you to start thinking about these pos, neg, 0 tokens as propositions in a propositional logic. Because when we make a complete lattice, there is a propositional logic hiding in there. Of course, you know about Boolean, Boolean lattices and hiding lattices and so on. Every abstract domain defines its own internal propositional logic, which gives you the expressivity of the properties you can state and validate with this machinery. And so that's why the selection of the abstract domain is so important. It gives you the range of expressivity. What can you talk about? So with the few minutes I have left, let's go forward into that idea. Going back to the original picture that started this presentation, here's our little sign domain, somewhat impoverished, but nonetheless, we do have neg 0 in pos. We have none in any, which you could actually think of as false and true, respectively. And if we start looking at this as if it were propositional logic, we know that the gamma map is defining a satisfaction relationship. Semantic satisfaction means a set of concrete numbers satisfies or has or makes true proposition little a, one of those propositions, if of course it's contained in the concretization, the image of gamma over a. And then syntactic entailment is of course just the ordering here. So the important point about that is it opens the door to ask us what else is in that logic over here in the sign domain. Soundness, of course, is again postcondition transformer. I mentioned all this earlier, that reappears. But here's the cool part. Gamma should preserve the meet operation in the abstract domain as intersection in the model domain, the power set domain, which means that meet is logical conjunction. And thank goodness for that, because it means that and works correctly in the world of abstract interpretation. And so indeed, just the obvious point is that the way conjunction is defined, of course, in propositional logic is saying exactly that gamma preserves meet in the abstract world. And that must be the case when you have a Galois connection. So that's another reason why we want this Galois connection machinery. Sometimes people complain it's a little arbitrary. No, it's not really, because if you want to think about this as doing something logical, you need that. Now, what about OR? Is it the case that gamma will preserve join as union, therefore giving disjunction? Sometimes it will, but it doesn't in my example. My little sign domain is so impoverished that if I take this join, that goes to any, and that concretizes to way too large of a set. And so this is not unknown to define a collection of properties and find that gamma does not preserve join as union, which means you cannot prove OR propositions with your abstract interpretation. And oh, that's maddening. Certainly maddening to the people who work with BLAST and SLAM. So the trick, at least the mathematical trick, you don't implement it this way unless you're forced into the corner, is to complete the original domain with what you call a disjunctive completion or downset completion or an ideal completion. You lift to sets. And each one of those sets in my enriched domain are down closed because of the monotonicity properties, but you can read those commas as ORs. And you can see, in effect, I have forced the OR operation into the domain. So this is disjunctive completion, and this is implicitly what happens inside BLAST and SLAM. They're working with an and/or disjunctive normal form logic based on the original primitive propositions, which in my case were neg, 0, pos, any, none. The Galois connection lifts in a very simple way. Gamma lifts into something called gamma bar, very trivial. Alpha lifts into something called alpha bar O because this is an over-approximating Galois connection. And the cool part is we have a little baby and/or logic. And so that's good. But we got more. We can go further. If you're a logic programming person and you're doing what's called groundness analysis, you actually need intuitionistic implication in your abstract domain. And so what you learned when you studied intuitionistic logic about Hutting lattices, you use it here if you're doing analysis of Prolog programs. You need that stuff. And if you're Muli Sajiv and you built the TVLA analyzer, you in fact have full propositional intuitionistic logic in the abstract domains that you use. So I'm just mentioning that. You can go back to that later. The key idea is that gamma tells you everything. The gamma map tells you which connectives, which operators belong to your logic. And what's interesting is sometimes those operators are surprising. So with my baby sign domain, it had just, my original sign domain had just this baby stuff before I did disjunctive completion. I knew I had and I knew I had these guys here, neg, 0, pos, any in my logic. This is cool. The negate sharp operation is a logical connective because it is a gamma. Gamma acts as a homomorphism, gamma completeness with respect to neg sharp. And that means you actually have a logical operator, a logical connective that could be of use to you. Now, this is not the usual negation that you have in a Boolean lattice. This is negate sharp, and negate sharp, as it says there, flips pos to neg. One proposition gets changed into another. This proposition gets changed, this proposition gets changed. And you can start talking in the logic of your abstract domain. And this is so important in practice. You've got to choose your abstract domain so you can talk about the properties that matter to you. So every abstract domain with its gamma map has its own internal logic with respect to the gamma. And a standard trick when you want OR in there is to do the disjunctive completion. So if you ever decide to go to work with building these sorts of things, please be thinking about this. But you've already heard enough that you can go to a meeting like the Static Analysis Conference and you can bluff now. Because you've seen all the key stuff now. Wow, we can apply this to calculate post conditions. You can find that so far I've been working with this kind of situation. If I turn the orderings upside down, instead of calculating post conditions that over-approximate or cover or are closed set representations of properties, if I turn this thing upside down, turn the ordering upside down, gamma bar survives, alpha changes a bit, I get an under-approximating interpretation which can be used for calculating preconditions or topological open sets or interiors. And so there's this beautiful duality, and that is useful because sometimes, well, if we're calculating preconditions, you have to do all of this machinery with the under approximations. And you can define what the model checking people call, like, they call it their abstract model checking logic, which is usually not the internal logic. It has to be narrowed down using the tricks I've just flashed by. But I do know the time's running down, and we got to get to the last part. Otherwise, I've not earned my lunch here today. We've gone now through the principles, and I've emphasized the fact that when you make this collection of properties, there's a logic there. And I've also pointed out that people have implemented these things and used them with massive pieces of software. And this is the last part that I'm going to try to develop before we're out of here. It's a little bit discouraging to find out that some of the biggest successes is just to take a big hunk of program and analyze it all at once. But this does work. This machinery is highly automated. If you have one human who can look at the results of the analysis and maybe make some internal annotations, it's surprising how much progress can be made. And so in particular, C programs, say like the Linux kernel, have been analyzed by just doing an abstract interpretation, much like you would say like type checking works, because you have a very simple one-pass analysis over all the code. You ignore the control flow structure. You don't care about how many times a loop repeats. You don't care which branch of the conditional is taken. You just assume all the code's going to get executed. You union together a bunch of constraints and you solve them quickly. And this has worked great for coming up with approximate descriptions of points to analysis in C. And then that information is used to validate other safety properties of C programs. So people do this stuff and it actually works. So you don't even have to worry about modularity if you don't want to. Dawson Engler, who is an operating systems person from Stanford a few years ago, took some really huge hunks of software, Linux kernel style stuff, and he tried to do model checking on it, and he tried to do this form of simplistic abstract interpretation on it, and he said this won, because with model checking, the model checker got lost in all these details, examining all these different orders of control flow execution, and it soon hung up. And so Dawson said, well, then I had to make an abstract model, and I left out some details, and I messed up. He said, this stuff gave me complete coverage. It didn't go very deep. It didn't tell me sometimes really interesting, weird counterexamples, but it was able to validate basic safety properties. So people actually do this. What about modular analysis? I got a couple of minutes here, and then I think I've used up my time. The idea which has been explored, and this is still under exploration, this is hard, it's hard for all of us, is to think that each component needs to be analyzed separately and a summary needs to be built. Some kind of table, some kind of collection of inequalities, something which describes what happens inside that component. The key idea is that when you analyze that component, at link time, you don't want to re-enter the code and reanalyze the component. You want to take the summaries from the link components, combine them, and then if you have to analyze those or compute a fixed point over those, do that. But don't re-enter and reanalyze code. That can be a challenge, because that means you want to solve as many internal local loops or fixed points in the components as possible, so that you gain some real speed up in doing this idea of separate component analysis. This is a huge challenge to do right. I'm going to try to give you a few suggestions about this. I'm not going to do terribly well, but I'm going to try. You might be familiar with strictness analysis or termination analysis. I'm going to use this one because I can pretend that a function in a functional language is like a component that links to other components, takes other functions as arguments. And so we have this simple typing system. And so, of course, in strictness analysis, we might say that this value means that the argument or the value might normalize, and the other value here means definitely it's not normalizing. And so for the base domain, like integers or booleans or whatever, there are just two options, two properties we might want to track. And so if we have a component that's parameterized on a base value, here are the options of how its termination behaviors would behave. There's only 3 of them. And then you go up one level higher in the ordering, there are actually only 6 different functions thanks to monotonicity with regards to how termination operates. With such a simple base domain, it is not unrealistic to just enumerate as the summary of this component the entire function graph. And that's what's happened here. Down at the bottom, I've taken this program here, F, which takes two external inputs, but they're both first order, and I've abstracted it to F sharp, which is tracking termination possibilities, and I find that here are my options. And this is somewhat similar in spirit to what predicate abstraction is doing, because this is trying to track a property or an invariant. In this case, the property is will not terminate. So you could imagine if you want to do global invariant checking across an entire system, you could set up domains with this kind of hierarchy. There are some details to be filled in. Here's an example more challenging like what we confront. I might have a component which is parameterized on another component as well as maybe a base value, and it does something like this. And if I enumerate the complete graph for this component, yeah, it's kind of huge. It's got 12 entries. But that's kind of like what model checkers do. They just enumerate the possibilities and exhaustively check them. This will actually get you some mileage for medium-sized programs. It really will. But if you're going to programs that are hundreds of thousands of lines, you got to do something which is a little more clever if you get it to scale up. And so there's a notion of frontier, which is a partial summary. Those people who have studied strictness analysis know that you don't have to carry around the whole graph for a component. There are only some entries in the middle, which are the critical ones, because they kind of predict how other arguments that are a little bit smaller or a little bit larger in value will behave when supplied. And so you can imagine an incremental accumulation of a summary which saves only values that are distinctive or tell you more than other values in the graph summary. And that's what a frontier is. And so if you go away and study the paper by Chris Clack and Simon Peyton-Jones, they have a very nice explanation of why it is you don't have to save the whole graph. And the reason the reason is that there are properties of monotonicity. That if you have some entries that you've saved, then other values which are similar can be predicted. So here, if I have an argument that's a little smaller than one entry I've saved, I know that the answer from that slightly smaller argument is going to be covered by this value here. And so I might, for that previous example, squeeze down the summary of 12 values down to the 3 on the bottom of the slide. And those 3 are pretty useful. From those 3, which I've repeated over here from this original example, and there's my hierarchy of domains, I can make all these other cool inferences. And in practice, that's what happens. When people are building modular analyses, static analyses of huge systems, what they'll do is they'll do it incrementally. They will lay out a component, and frankly, they'll put together some sort of skeleton information. And as that component is inserted or linked to other components, that generates more needs for more summaries. And so finally, you can start with symbolic evaluations, and this is where the state of the art is, that you have a mixture of symbolic evaluation generating these instances or increments. So it has a feeling of partial evaluation where you build up the modular information. I don't have time to talk about solving local fixed points, but it has something to do with approximation, jumping to limits, and that's an idea that if you can master it, it's really cool. But in practice, what happens is that we can take techniques from symbolic evaluation, marry them to this frontier idea, and get a lot of mileage out of it. What up there is a link to this talk, as well as the papers that I've drawn from the most, but the literature is just huge. And so I hope this gives you an idea of how this foundation works, how it's been applied, and how it can be relevant to analyzing properties or extracting properties from language definitions as well as particular programs. So yeah, I think I'm ready for questions here.